Welcome to the second session of PEPM 2024. In this session, we will have 4 talks, and our first speaker is Tomoaki, who will be talking about a library for stream processing. And this paper was selected as the best paper, distinguished paper of this year's workshop. So congratulations. Okay, so please start your presentation.
Yeah, thank you for the introduction. I'm Tomoaki Kobayashi, a master's student at Tohoku University. This is a joint work with Oleg Kiselyov. Today, I'm going to talk about a paper, Complete Stream Fusion for Software-Defined Radio. In this research, we evaluated Strymonas by software-defined radio. Strymonas is a declarative stream processing embedded DSL, an implementation given by OCaml, and it can generate efficient C code. This feature is thanks to complete stream fusion. Let me show an example. Strymonas from the left declarative pipeline can generate the right imperative efficient C code. This C code is efficient because it has a single main loop and no dynamic allocation at all. In the past, Strymonas had evaluated only by small micro benchmarks, and we didn't know complete stream fusion is whether complete stream fusion effective in realistic applications or not. So in this time, we evaluated Strymonas by large macro benchmarks of SDR. Especially, our goal was to confirm performance on real-time FM radio reception of Strymonas. FM radio reception is described like this. Now, as I input, FM signal is given. Typically, it is in 1 to 100 mega samples per second, and it is processed by low-pass filter and FM demodulator, and finally, it is passed to sync, typically in 48 kilo samples per second. In this research, we implemented FM radio reception of Strymonas like this. And this implementation corresponds to FM radio reception of the most popular software-defined radio framework, GNU Radio. So low-pass file source, low-pass filter, demonstration, and null sync. With the basically same pipeline as the result slide, we can listen to actual FM radio on Strymonas. Now I play back a pre-recorded result of a Japanese local station. This is a noisy but certainly intelligible result. Upon realizing this application on Strymonas, we encountered a challenge. That is, Strymonas doesn't provide windowing. Windowing is a combinator which takes a stream as an argument and returns a stream of window. Window is a history of recent data and required by many digital signal processing operations of software-defined radio. This is such an operation, FIR filtering. Here, Xi is the current input, and Yi is the current output. Then, when computing Yi, M samples from Xi minus M minus 1 to Xi are required, and with windowing, on Strymonas, filtering can be implemented like this code. Windowing on XS, then map. This is what we wanted to do. So the accompanying questions are as follows. Can we express windowing with the current Strymonas? Does it require an extension to the existing primitive combinators of streaming? And in that case, what about complete fusion of windowing? And if we can express windowing, then does the expressed windowing have high performance? Is it sufficient for real-time radio reception? We addressed the challenges by designing a high-performance windowing. It guarantees complete fusion by construction. Using this windowing, we evaluated Strymonas by FM radio reception on a relatively low-end platform, Raspberry Pi Zero. And it was faster than the state-of-the-art GNU Radio, and it attained real-time FM radio reception. This is how we addressed the challenges. Strymonas supports by nature stateful streams. So it means Strymonas can handle state-free Windows history management. And its existing primitive combinators turned out sufficient to implement windowing. That is not to say easy. A lot of effort went to generate C code that is optimal or optimizable and vectorizable, as I will explain later. And since we managed to express windowing via existing primitives, complete fusion is assured by construction. For windowing, we generate code specialized to window size and sliding or tumbling. There's no time to go into detail, so let me show just a simple example. Cyclic buffer is a straightforward implementation of stateful window. In this case, access to a buffer in generated code becomes an operation of loop index I and bit mask. And this access is too complex to automatically vectorize by C compiler. And under some specialization conditions, we generate a windowing code whose Windows allocates buffer twice the needed size and copy from time to time. In this case, all loops have constant bounds, and all index expressions are I plus const. This is easy to optimize and vectorize by GCC or clan. Now we have a high-performance windowing. Using it in evaluation, we compared Strymonas generated C code and GNU Radio C++ code on Raspberry Pi Zero. There are two types of evaluation. One is FM radio reception benchmark. This uses the application on the result slide, and its source loads a file of pre-recorded 3 seconds FM signal, and sync just throws away its input. So it means it do nothing at all for input. And another evaluation is real-time FM radio reception. This it uses basically the same application of the benchmark, but source and sync are different. Now source becomes an SDR receiver connected via USB, and sync becomes an audio player. As for FM radio reception benchmark, this was the result. There are two variations for source of the pipeline. Preload means preloads the whole file while the reception. And include means incrementally loading the file block by block while the reception. And all runtimes were less than the loaded file's 3 seconds. And as you can see, Strymonas was twice or more faster than GNU Radio's runtime. This is the result of real-time FM radio reception. Strymonas had a little unstable and noisy, but intelligible playback. And GNU Radio had unstable, noisy, and unintelligible playback. Related work is as follows. StreamIt is a standalone DSL of stream processing. Its execution model of stream processing is based on static scheduling and synchronous dataflow. And it has split and join operators for streaming. On the other hand, Strymonas is an embedded DSL, and its execution model is based on push and pull-based streaming. GNU Radio is a state-of-the-art software-defined radio toolkit, and it is actually a C++ framework. We can use GNU Radio by writing C++ code or Python binding code, or drawing block diagram in GUI toolkit. When using block diagram, GNU Radio generates C++ code or Python binding code internally. Unlike the Strymonas' code generation, GNU Radio's code generation has little type safety, and bugs are easy to introduce. And GNU Radio's processing is scheduled by thread per block scheduling. So it means it has multi-threading. On the other hand, Strymonas processing runs on single threading. In conclusion, we designed a high-performance windowing and evaluated Strymonas by FM radio reception on Raspberry Pi Zero. As for future work, there are many things, but what I want to try right away is high-quality sound real-time FM radio reception. This is the end of my talk. Thank you very much for your attention.
Thank you. Any questions?
Do you have a little recording of your things you presented to us, this 5 seconds music or whatever? Do you have the improved version of it? Is my
Sorry.
During your presentation, you make us to listen to 5 minutes or to 5 seconds music or whatever.
10 seconds.
10 seconds. Do you have the same thing after your processing? You're improving, throwing away the noise of that.
This was the best version. Was this the best version?
Yeah.
A lot of noise in that. Didn't you? So can you reduce
I
that
noted
noise?
that
Not with picture, with sounds.
this noise is due to this live sound processing, and we haven't tried high.
Okay.
Yeah.
Now
high
you
quality
process
sound.
that, you improve that, the quality of that broadcasting. Can you make us to listen to the improved broadcast?
But I think you haven't actually done this future work. Improving it is future work, if I understand.
So currently you have the versions of noisy So currently you have the noisy version of the FM radio, right? So do you have you applied your tool on this noisy FM radio to show the difference between the baseline and your improvement?
So
Yeah. So
I think what he's trying to say is that GNU Radio produces the same noise due to naive audio processing, and actually the result is that his method is faster, not that it produces less noise.
Okay.
I'm not sure. I'm not so good at English conversation. Sorry.
So the improvement is that your audio processing or your streaming is faster. Your stream processing faster, but you're not producing less noisy radio signal, right?
I may be sure what you are asking for me. So for high quality sound processing, it requires speed, but my current implementation is so slow, and you consider this is a kind of issue, maybe not?
Kind of.
Sort of.
Sort of? Sorry.
Yeah. Okay. So the question is sort of your Strymonas processes the signal faster than GNU Radio, right? But it doesn't reduce the noise. It has the signals, the output signal of GNU Radio and the output signal of Strymonas as the same signal.
With the same input, GNU Radio.
Yes, the same input, but it's not the same
With
output.
the same input, GNU Radio and Strymonas generates basically same input without computation error.
So only speed is improved. Only speed is improved. Is it correct?
Yeah, actually.
But
yeah.
as long as the speed is enough to follow the human conversation, and don't need faster processing. You see, there is an intrinsic limit. It's not necessary to go faster and faster, as long as you keep up with the pace of signal of human voice.
Okay.
Or whatever. Maybe, okay, yes.
GNU Radio result was unintelligible, so speed is, in this case, is so important.
But unintelligible is not a physical quantity. You have to tell us the power of noise. A number is necessary. Unintelligible is because maybe it's another language, it's English, I'm expert in Italian. Unintelligible is not a physical measure.
Thank you.
Would the same approach work for AM or shortwave broadcast? You can listen to it here, like BBC shortwave in London. Do you have to have some special hardware to do this?
You mean you tried BBC radio reception
Now?
here?
Yeah.
I haven't yet.
Try it. Oh, okay.
Yeah. But I want to later. Thank you.
Any other questions? So we have this certificate of this award. So congratulations again.